Okay, let's talk about electric fields. If you remember a while ago, we took some masses and we hung them on a spring scale. And when we did that, we found the force on them. And we took that force and we divided by the mass. And it gave us a value of newtons per kilogram. And we found something around 10 newtons per kilogram on the surface of the Earth. And we called this the field strength on the surface of the Earth. What is field strength? Field strength is literally how strong a field force is. What is a field force? A field force is a force that is not a contact force. Magnetic forces are field forces. Electrostatic forces are field forces. Gravitational forces are field forces. They can push or pull you even when you are not in contact with them. The Earth is pulling down on me even when I am jumping in the air and I am not in contact with the Earth. Well, turns out we can measure the field strength at various points, even for charges. Imagine I have two charges. Just charge one, we'll call this big Q1 and big Q2. And they're both positive. I know that since they're both positive, they will both repel each other. Depending upon how far away they will repel each other with different strengths. If they're very, very close, they'll repel each other with a lot of force. If they're very far away, they'll repel each other with a little bit of force. That means at different distances, the strength of that force is different. And so at different distances, the strength of the field is different. Let me give you a very clear example. Here is the Earth. When you are standing on the Earth, you maybe weigh 150 pounds. Then you go out into space and you think you have no weight, but in fact, the Earth is still pulling on you, because if I put you out in space right here, you would find your way back to the Earth. We already know, because we've calculated this before, that if I maybe double the distance, I get this quartered. So I'm going to go from, 150 pounds to 37 and a half pounds, because I went double the distance away. And that's how fields work, right? That's how field forces work. It's over this r squared. Double the distance, I squared 2. So it became over 4. I divided 150 by 4. Same thing is true with electrostatic forces. When I'm talking about the field surrounding the Earth due to gravity, that field points towards the Earth. Gravity points this way. Gravity points this way. Gravity points this way. Gravity points this way. And now when I'm talking about the strength of the field, these field lines that are pointing towards the Earth can actually help tell me the strength of the field. The distance from here to here, we'll call this distance 1, is smaller than the distance here, distance 2, is smaller than the distance here, distance 3. So the closer together our field lines are, the stronger the force is. Well, it turns out for charges, for a single charge, our field lines look very, very similar. Here's a charge Q. Before I put arrows on it, I'm just going to say, I know the field lines do this. I know they point either out of it or into it, and they go like this. But remember, when I had the Earth is always pulling objects towards it, because that's how gravity works. Gravity can only pull. What about electrostatic forces? Electrostatic forces can pull things, and they can also push things. So because they can do both, how do we decide which way the arrow should go? And how do we decide, what we should use for a convention? Well, someone came along and they said, I'm going to use a positive test charge. I'm going to pretend that I always have this little positive charge that I keep in my pocket. It has no mass, and it is positively charged. And all I'm going to do with that positive charge is I'm going to put it down on the page, and I'm going to see where it goes. So I take my small positive charge and I put it down right here, and I see which way it goes. And if that positive charge gets repelled, well, then I know my lines point that way. And that also tells me something, doesn't it? If I have a positive charge that gets repelled by this, it tells me that this is positively charged as well. So when oh, sorry, you can't see this one. So when I have field lines that point out of stuff, I know that that thing must be positively charged because I used my positive test charge and put it down. Well, what if I had put down my positive test charge and instead of being repelled, it had been attracted? Well, then I know that that thing is going to be a negative charge, and the field lines point this way. One thing you will notice between positive and negative field lines is they look exactly the same. The only thing that's different is the arrows. So without the arrows, you don't know whether the thing is positive or negative. Without your small positive test charge, you don't know. If you're just looking at the field lines without the vectors on them, without the arrows that represent it, there's no difference between a positive charge and a negative charge. They both just look like this. Okay, I'm going to show you one situation of, well, I guess I'll just show you the most common situations. Most common situations, I have a positive and a negative. So what do? I put my positive test charge down. I put it down right there. What's it going to do? It's going to go right towards a negative. It's positive. It's repelled by that, attracted by that. I put it down right here. What's it going to do? It's going to be like, oh no, I got to get away from this positive charge and start to go this way. And then it's going to say, hello, I want to be next to you. And it's going to go like that. Same thing on the bottom. And so all in here, our field lines are going to look like this. Imagine those arrows aren't there. There's no arrows. Goodbye arrow, goodbye arrow, goodbye arrow, goodbye arrow, goodbye arrow, goodbye arrow. Can you tell the difference between which one is positive and which one is negative? No, they look the same. It's symmetrical on either side right here. You can't tell the difference. It's only because I put down my positive test charge and I, as a human, decided I want other people who look at this to know what I'm doing. Because what if you didn't have those? This could be a real question. Which is the positive charge? Which is the negative charge? Well, you know that field lines point from positive to negative, and so you know that they are both different. Sorry, you know that one is positive, you know that one is negative. And you know which is which. Another common scenario. Two positives. All right, I'm a positive test charge, and I'm going to go down right here. Not quite at the center. I'm going to put a dashed line for the center just so we can see where the center is supposed to be. I'm going to go right here. I'm a positive test charge, and I'm like, oh, I want to get away from you, so I start to move away. As I start to move away, I'm like, I really don't want to get close to that one either. So I start to curve, and then I run away from both of them. And the further and further away I get, the more they look like one tiny mass that's together, one charge that's together. The further away you get from things, the closer they appear to you. And so when you get sufficiently far away, you're basically just running perfectly straight away because they appear to be one thing. It's going to look like the same on the bottom. Okay? We're running away. We're running away. I am first running away really strongly from the thing I'm closest to, and then I start to notice that the other one exists. And so I start to curve away from the other one also. Hey, what if this were negative? What if they were both negatives? Would it change anything? It would only change the direction of the arrows. The lines would look the same. I also want you to notice right here, there's a gap. The field lines can never cross. They're never allowed to cross. I can never do this. That doesn't work. Field lines will not cross. And so what happens is I get this little region of space where the positives effectively cancel each other out. And so if in this tiny little region of space, I put another positive charge, it would just hang out. It wouldn't do anything. Or if I put a negative charge, it would hang out. It wouldn't do anything. Because those two things cancel each other out right there in the center. What if these were negatives? Well, the arrows would just point the other way. And again, look, without the arrows, I have no way of knowing if this is a positive or a negative charge. I have no way of knowing. Couldn't tell you, but if I know this is negative, I know that my small positive test charge will be attracted to it, and so the arrows will point towards it. Whoops. And so now I'm going to show you this little simulation that I put on the website as well. Okay, so basically I've got two charges, charge 1 and charge 2, and I can change the value, and I don't know if you can see or not, but red is going to be positive. If I make them both 0 and 0, no field lines. Charge 1, I make positive 1. There are my field lines. You can see that they're pointing away. Let me zoom this in a little bit. You can see that they're pointing away because it's a positive charge. If I make it negative 1, now they're pointing towards it because it's a negative charge. And my positive test charge will be attracted. If I give them both the same charge, there it is. Even if I give them both positive 1, it's going to look exactly the same as when they were both negative 1, the arrows just point the other way. And again, if they're opposite, one is positive and one is negative, one, it's going to look like this. I don't think the Regents was going to give you a question where you have more than one. As far as for drawing field lines.